today. I will start giving some motivation and the results we have, predictions we have for the standard model light-by-light scattering that we had in the past years. And afterwards, I will just present the very recent experimental evidences we have for this standard model results. And after that, we have some good motivation to start working in the new physics point of view and trying to use this production channel in order to look for deviations from the standard model. And I will present a very few examples just to show how these these predictions can help to understand some other theories beyond the standard model. And then I show later the experimental motivations we have to seek for these signals in CMS using this 4 detector. That's the CT-PPS detector. So just to give you a broad view of this physics, the gamma-gamma physics that we have to produce low mass pairs or high mass pairs. We have so far many different results from all the LHC experiments so far. I will just them a bit just to remind people of these results that we got out since I think 2011. So until now, 6 years, we have many works reporting results for the gamma-gamma physics. First one from CMS is the gamma-gamma production of E plus E minus pairs that happened in 2011. And afterwards, we have the dimuon production in the same mechanism. And afterwards, we start looking into high mass pairs producing WW bosons using the gamma-gamma physics. So we use the dimuon channel as a benchmark in order to understand the selection and all the physics involved in this measurement, and then we move it to the WW production in order to have some study on this production mechanism. And later in the next analysis, when we move from 7 TeV to 8 TeV, we started to have some evidences of this WW production in 2-photon fusion process. So this is the first evidence. We are looking for a real measurement of this process. But so far, we have achieved a very good capability to measure this kind of processes at high masses. Atlas also has reported the same results a bit later. And then we have other results from Atlas looking for dilepton production at 7 TeV and then dimuon production at 13 TeV. So we are covering from energies from 7 TeV to 13 TeV producing low mass and high mass pairs. And we have a very good knowledge of these processes in the standard model. But the main idea is that what about processes that involve 4 photons? So we have looked at so far production of high mass bosons or fermions, but haven't looked at this kind of process where we have light-by-light scattering, which is a motivation that since many years people are proposing different experiments to check this kind of process, which is not predicted by classical electrodynamics. And QED is seeing this kind of process at second order. So you're trying to look for this kind of processes. So if you're looking for a one-loop mechanism that produces 2 photons, we are looking for box diagrams involving leptons and quarks as fermions, and then the contribution from W bosons as in this loop. So we are looking for this kind of light-by-light scattering at the one-loop level. And we can differentiate these 2 processes when you look into the fermion loop, which dominates in low mass invariant mass, or high invariant mass when you include these W loops. So I show it a bit later in more detail. And then this kind of process can lead to some discoveries in beyond standard model physics, when you have a kind of mediator here that can couple these 2 photons to the 2 finite state photons. So it's a nice opportunity, and we have the experimental capabilities to look into this kind of processes, so why not investigate these guys a little more. So until now, we had some ideas to study experimentally some evidence of light-by-light scattering. So it comes so many years ago, and starting to propose some kind of a way where we have 2 crossing beams of photons that can interact with each other. So the main idea, the first idea was using the Compton backscattering in order to look for these kind of evidences, but so far we have no direct evidence of this interaction between photons using such a experiment. Other proposal involves using cavities. So the idea here in this work was to try to obtain a very high electric field strength inside the cavity in order to have interaction between the photons in these fields. But as before, there is no evidence of this interaction. And later, another proposal using high-power lasers, where you can have interaction point here and then try to achieve some very high electric field strength here in order to have an interaction. So the idea is that if you have a very high energy electron, you can go close to the critical electric field strength at this point, and maybe you can be able to prove light by light scattering. But unfortunately, no evidence has been found so far. And the last and main trend idea now is using the photon colliders in order to look for this kind of process. So this is an idea that is coming like 20 years ago, but the plan is now that we have LGC, you have very energetic colliding particles, you can have an opportunity to look into this kind of process. So in this previous idea is similar to the Compton backscattering, where you have a laser pointing to the electron beam, and then you try to extract a photon that you interact with another photon, and then you have try to look for some light by light scattering. But so far there is no evidences. There are no evidences of this process. But this is an opportunity you have, and you are looking for this kind of process at the LGC. But the idea is a little different than having a beam of particles or two lasers that are pointing to an interaction point. So you are using that our particles, protons or nuclei, that are charged and then have very intense electric fields in the transverse direction, given the relativistic movement of these guys. So in this case, we can have very intense electric fields here, something close to 10 to the 14 Tesla, and then you can have some interaction between photons here to produce pairs. So this is the main idea we are using to studying dileptons or diboson production. So then the plan here is to go one step further and try to look for light by light scattering using the same process. But in order to ensure that the overlap of these two colliding particles are not probing some QCD interaction, you have to ensure that these two guys are very far away in order to avoid the QCD interactions and then just to enlarge the interaction of these photons. So we have to ensure that the impact parameter in this case is larger than the sum of the radius of these guys. So in this case, we have great possibility to have photon-photon scattering and then suppressing the QCD interactions to avoid any contamination in our results. So and then the idea when we are looking for these two colliding particles, we are usually for the proton a form factor, electromagnetic form factor, we have to be sure that these photons that are being emitted by the colliding particles will produce centrally a system that will be of our interest. So we basically use the same collinear factorization, and we split from the parts that come from the photon fluxes, which is these F functions here, x1 and x2. And then you have the elementary cross-section for the process we are interested in, dileptons, dibosons, or gamma-gamma to gamma-gamma. And you use the same idea, the same recipe you have been using so far for many of the high-energy collisions you're looking at LGC. But the interesting fact here is that we have a photon flux, that is the probability that these photons will be emitted from the colliding particles to produce a central system. And these photon fluxes are very high at the LGC kinematical regime, especially in the case of nuclei collisions. Because each nucleus has Z protons, and then this photon flux will be enhanced by a factor of Z to the 4th. So then we have a very large photon fluxes from the nuclei collision, and then you have an enhancement of this cross-section. Total cross-section here for nuclei is much larger than the proton-proton, and this is the reason that we are looking for this the production of light by light scattering in lead-lead collisions. So then the plan is we start presenting the predictions we have so far for the standard model light by light scattering. So we have done this work a few years ago, and there are very good experimental evidences now that motivate us to keep looking and improving these results, but also looking forward and trying to look for beyond standard model results out of this gamma-gamma to gamma-gamma scattering. So in this proposal, we were looking for the production of light by light scattering using the same recipe from the collinear factorization, using 2 photon fluxes from protons, either nuclei, in order to produce the 2 photons in this kind of process here. We investigated first the case of proton-proton collisions, proton-lead collisions, and then later the lead-lead collisions to see which case would be the most favorable to see this kind of process. Reminding you that there is no evidence so far of this process measuring in any laboratory. So the idea here is to motivate people to motivate people to look for this process at the LGC, because the chance to see this for the first time in this process was very, very good. So the idea following this total cross-section is that we know very well the photon fluxes, and the elementary cross-section is known since a long time. We know the first order calculation for this one loop amplitude. We can include also the QCD and QED corrections. However, the idea to including these guys is suppressed by the rapidity gap survival probability that will be reduced to the cross-section in between 20 and 10%. So if we include the corrections, we will be overlapping by the reducement in this survival probabilities. So the idea is either using both or not. So in these results, we decided to use only the first order calculation and then leave away this rapidity gap survival probability. And since many particles decay into photons at low mass and the low mass region, like light mesons, so we decided to look for this kind of process with an invariant mass above 5 GeV in order to look for any signal that are above any resonances of low mass mesons. So then the idea is to look for low mass invariant mass systems and try to favor one of these kind of collisions that you can achieve in the LGC. So then with our results, we were able to calculate the cross-sections for all this process and estimating a few events that we can observe at LGC. So you can see that the cross-section is much higher in the case of a lead-lead collision, that is the red curve. So the other possibilities are orders of magnitude lower, but you can still have to still include some selection on these events. So and then you are going to see that there are no many difference between the 2 lower guys, proton-proton and proton-lead collisions, but enhancement by lead-lead collisions is very, very interesting, because then we can have a larger number of events expected in any of the LHC experiments. So we are using a lot of parameters here to ensure that we have gamma-gamma to gamma-gamma interaction in order to produce this final system here. And always looking for invariant masses above 5 GeV to avoid any low mass resonances. So the idea was to provide some predictions, very realistic for the LGC kinematical regime. So we used MSC generator, that's MADGraph version 5, to make some free advertisement here. And then we have some event samples in order to look for these events with gamma-gamma final state. So in order to constrain the kinematic regime to that possible to be seen at the Atlas or CMS, we restrained all events to be within the pseudo rapidity below 2.5. And the forward direction, we also included a cut on the pseudo rapidity for the calorimeters in order to have a clear signal of exclusive gamma-gamma. The pile-up effect is more pronounced in the case of proton-proton collision. So in this case, we have took only 1% of all the luminosity expected for proton-proton collisions. In P-lead and lead-lead is more favorable to have fewer overlap collisions, so we can keep just all the luminosity for these kind of collisions. So for the trigger efficiency, we have taken all the 100% efficiency to look for back-to-back photons. For detector acceptance, we have used the Monte Carlo sample in order to estimate what would be the acceptance in both Atlas and CMS experiments. And reconstruction is a typical efficiency of 80% on the photon measurement. So combining all these effects, we have a global efficiency in both cases, nearly between 12% for PP and P-lead and 20% for lead-lead collisions. So this is what we are going to use so far to restrain our selection to look for light-by-light scattering in lead-lead collisions. Yeah. Sorry? You mean the separation between them, or? Usually we are applying a difference between like 2.5 or something in order to ensure that we have a rapidity gap between them. Yeah, yeah. And okay, so then in order to isolate our signal and reduce the effect from background events, so we have many sources of 2 photons that can contaminate our final state signal. So we are just looking for 2 isolated photons within this pseudo rapidity and mass above 5 GeV. We are suppressing no other charge particle activity, no hadronic activity in the calorimeters in order to restrain these results. So all the diffractive and central exclusive production of photon-photon are suppressed, and then you keep only the gamma-gamma to gamma-gamma signal in this case. So basically we apply a PT cut on the photon pair below 0.1, and this variable that we call complementarity is below 0.04 in order to ensure that we have very elastic case and gamma-gamma to gamma-gamma process. So using all this suppression of backgrounds, you can see in this table on the left that we have a much more favorable result when we include the lead-lead collision in comparison here, light-by-light scattering by other backgrounds. This is the central exclusive production is by far the larger contamination we have in this signal, and we can see that the better case to look for light-by-light scattering is using lead-lead collisions. So using this selection, the result is this number of events we're expecting at LGC, and lead-lead collisions has more or less 7 times more than expected for PP collisions. So this is why we motivate in this work to look for lead-lead collisions for light-by-light scattering. So if we put everything together in the Monte Carlo sample, after applying all the selection, you see that you have the signal of gamma-gamma to gamma-gamma much more enhanced than the background events. And also we extended these results for the FCC kinematic regime, which will achieve colliding energies much larger by a factor of 7, more or less, than the LGC. And the idea is that the enhancement of the photon fluxes will increase the production cross-section, and we expect to have many more events of this process. So you can see that the statistics is much better in FCC, given this enhancement of energy, and we expect to have a much more clear result. So if we have any chance to have an evidence of this process at the LGC, we can study further its properties at the FCC. Sorry. So here, sorry, I forgot that. Yes, GeV. So it's 100 GeV. 1 point GeV. No, yeah, because you're looking for back-to-back photons. So we expect that the PT will be very small. So it will be centered in the 0 PT, and then we expect to clean all these backgrounds that are above this cut. We can when we have this distribution. If you have enough events, we can do that. If you have good statistics, but no, that's not a problem. I forgot just the unity here. Sorry, but then we can apply for the PT of the pair. We can apply such a cut with no problem. Okay, just so this summarizes our predictions for light-by-light scattering at the LGC and FCC. So it's just standard model results. So the experimental evidence we have so far comes from Atlas. That is the most recent result. Probably many of you have heard last September, I think. This is the nice results they presented at the Nature Physics. And CMS is also looking to these results with reporting similar numbers as Atlas. So very quickly here, I'm just showing the analysis they did with more or less 500 inverse microbarn of data using these 5 TeV lead-lead collisions. And they were able to see 13 candidates for this light-by-light scattering, just mentioning a standard model case, and measuring this cross-section, which is in agreement with our predictions. There's very good results because they are close to claim discovery. So we have 4.4 sigma in this measurement. So we expect that next year we can have some enhancement in this data sample, and then we can maybe claimed the discovery of this light-by-light scattering finally. CMS has also made analysis that is reporting 13 events as Atlas, so we're expecting just to have the final result soon, So here is just a distribution showing the data that Atlas have found in this analysis, and we expect that with a bit more of data, these results can be much more interesting and maybe claim discovery. So this is just an event display showing the two photons. They are very back-to-back in this transverse plane here. So the idea is to ensure that we have a gamma-gamma interaction to produce these two photons, and you can see clearly that they are really back-to-back in this transverse plane. So then the idea is that, I cannot, it's very, very long. So the idea is that, okay, we have these measurements from Atlas and CMS. We have the central system measured, but then what about the protons? Because with this electromagnetic interaction, we expect to have both protons intact in the final state. So if you could be able to measure these protons, we can be sure that we can reconstruct the whole kinematics of the event. So this is a very nice motivation if we are able to measure these two outgoing protons here. That's these two arrows going close to the beam. Because during electromagnetic interaction, we expect that the two intact protons will be very close to the beam, that the trajectory change very little by a few milliradians. And we expect to have very close to the beam, very far, we can measure these protons. This is why I motivate this discussion, because later we'll talk about our 4 detector to measure these protons. But the main variable that we are looking here is the psi variable, which means that we have the P, that's the nominal momentum of the protons, and then you have delta P, that is the longitudinal momentum loss of these protons. So if it has some longitudinal, if you have some missing momentum here from this interaction, we can measure psi variable in order to attain this to a elastic collision by gamma-gamma interaction. So this gives us a very good sensibility to look in the whole kinematics of the event, and then look for very good sensitivity for beyond standard model search. So we can go from standard model to beyond standard model looking for this kind of process. So this is why I'm going to discuss a very some results that Christopher had talked in this morning, and I will show a few predictions for the standard model, theories beyond standard model. So we have various candidates for beyond standard model physics, and many of them can be produced in gamma-gamma physics. So there are known coupling of these particles or these proposals to gamma-gamma physics. So the idea is to search for any deviation in the standard model result in order to see if you have if you can have any signal of new physics from the standard model expectation. So as I mentioned before, we are looking for diphoton invariant mass very low, starting at 5 GeV, and then you can see that the contribution from the fermion loops that we are using, that is the green curve here, that's very difficult to see, you'll be overcome by the W loop contribution, that is the red one. And at high invariant mass, above 200 GeV, we start to have more contribution for W loops than the fermion loops. So the idea is that at this high mass region, we have different contributions that can enter here. And then in this region, we expect to have some signal of new physics. So the idea is that this region will be experimentally accessible with this 4 detector, and expect to have some new results here. So the idea is that we can look for gamma gamma to gamma gamma using a effective Lagrangian in order to look for anomalous couplings in order to predict some deviation from the standard model predictions. So the idea is that using these results that we had for gamma gamma to WW, we already have some put some limits on the anomalous couplings for gamma gamma to WW vertex, which are going from 10 to the minus 4, 6 to 10 to the minus 10 or 12, depending if you have used form factors or not in this case. So you can, there are studies, and we can expect that the gamma gamma to gamma gamma anomalous parameter will be sensitive to the order of 10 to the minus 13 and 10 to the minus 14. So in this regime, we expect to have some good results in order to have sensibility to look for these anomalous parameters in gamma gamma to gamma gamma interaction. And I mentioned later, we can have new particles that you make the coupling of these two pairs here, and we have considered some, there are some consideration on other particles from beyond standard model theories. So we can see that with the using the Monte Carlo, that's for the physics Monte Carlo, that is working with Christophe and other colleagues here. They have produced a event sample in order to analyze event mass of these photon pairs above 600 GeV. It's where you expect to have reduced the background from other production mechanisms, and applying some some kinematical cuts very related to the gamma-gamma physics that we have discussed at CMS, so we can eliminate other backgrounds. So at the end, we have here two curves in black showing the possibilities to produce this gamma-gamma to gamma-gamma physics using these anomalous parameters here. And you can see that only the gamma-gamma to plus pileup will be the main background. And the idea is that we can reduce this background by using a proton tagging experiment in order to have the measurement of this intact proton going outside the beam pipe and reduce the effect of this pileup here. So the idea is that reducing the red curve here, we can enhance our signal for discovery. So the idea is that once you have an experiment to tag this outgoing proton, you can have the kinematical of the event totally mapped. And at this moment, we are using a full detector in CMS that has this interval for the fraction of momentum loss. That is the variable I showed before for you, the psi variable. And then you have a matching between the invariant mass of the photon pair with the invariant mass of the measurement of these outgoing protons. And then we can, ensuring some uncertainty here, we can ensure that the two events are connected with the same protons. And in this way, we can have a significance of this result compared to the background of gamma-gamma plus pileup. So the idea is that using the proton tag, we can enhance the signal and look for the signals of new physics using these anomalous parameters. So here is the same two parameters as before. So summarizing everything in a table, you can see that applying this cut flow for including the matching with the tagged protons, you can have a result that is background free, and then you can have observation, very clear observation of this gamma-gamma to gamma-gamma event with some predictions using the anomalous parameters going to a range of 10 to the minus 13 to 10 to the minus 14 in sensitivity. So the idea is that with this kind of strategy, we can have very clean results for gamma-gamma to gamma-gamma physics, either looking into the standard model case with low masses or high masses for the beyond standard model physics. So beyond that, we can have also a complementary study using the gamma-gamma to gamma-z channel. So in this case, we can complement these searches for the anomalous parameters, including the gamma-gamma to gamma-gamma results. Actually, we can even include in these studies gamma-gamma to z-z and extend our results to gamma-gamma to WW. So really the idea here is that once we have some evidence for deviation of standard model in gamma-gamma to gamma-gamma and gamma-gamma to gamma-z, we can be sure that we are looking for the same signal from anomalous parameters in two different channels. So that would be a very robust result in order to show that we have a deviation from standard model. So in here, looking to this kind of final state, we have the same strategy applied as before, applying the kinematical cuts to reduce the effect of backgrounds, and then using the proton tag in order to reduce the gamma gamma plus pi lap background, and then you can enhance the signal and the significance here in order to have a measurement of this kind of process. So here we see that we have the results have used a colliding energy of 13 TeV, a total of 300 inverse femtobarn of data, and considering here this me, that is number of the pi-lap effect, so number of simultaneous collisions, that is taken as 50 in this case. We can really, in a very complex scenario, in high luminosity, we can have even a very clear signal of this gamma gamma to gamma z result. So and then summarizing the table, applying the same strategy as before, you can see that we can have a background-free observation here and have a very clear signal from this gamma gamma to gamma gamma z process, and even including sensitivity to the anomalous parameters, considering the lepton decay of the z or jet decay of the z, and combining both in order to have a sensitivity on these guys. So this is very interesting opportunity to look for all results in beyond standard model physics, looking for two different channels, so gamma gamma to gamma gamma and gamma gamma to gamma z. And just to give you an idea, I took it from colleagues from southern Brazil that are working in this gamma gamma physics. They are proposing the mechanism to produce a dilepton and a monopolium in gamma gamma physics. So these two guys can decay into gamma gamma, so you can have a signal of light by light scattering, so to say, using a resonance here that can be measured. So there are many predictions, even in proton-proton collisions or lead-lead collisions, considering these guys. So the monopolium was mostly a motivation after that very small resonance that was seen in 2015 of 750 GeV, which is very close to the mass of the two monopolions. So that's the idea, sorry, two monopoles. So the idea is that the motivation started there for these guys. So once you have sensitivity to look for gamma gamma to gamma gamma physics with a Ford detector to tag these protons, you can have a very good sensitivity to look for new physics. So then just to finalize, I have a few minutes, I'll just discuss a bit the, yep. Sorry. Here, you mean? From 100 to 250. Yeah. Is the total cross section? Yeah. I mean, the idea was to start looking into this. As far as I remember, the magnetic monopole has some 300. That's a good idea. No, I have no idea. If you are using, as I explain later, if you have an experiment that has a sensitivity above 200 GeV, it would be very difficult. Usually, depending on the optics and the way we align the detector, you have sensitivity above 400 GeV. So, is very difficult to. You are in the edge. Yeah. So then we are here is a bit below the threshold that we have the experimental acceptance. Yeah. I mean, I'm not very aware of this physics, so I'm just quoting the results. Yeah. Yeah, is a model dependent, so. Yeah. Yeah, that's you have just to multiply here by the Brayton fraction. Yeah. Wherever you want, you can try. But anything that you can increase the cross section to have some, because here you have also to include that they decay to photons. Here's just a resonance. So if you consider that, sorry, that the monopolium is decaying to photons, have to just to multiply the Brayton ratio. So it's, yeah. Mm-hmm. I mean, the paper is quoted here if you wanted to have a better look. So in the no, sorry, before. So, but you can check the paper and they discuss it. I miss it now. But as Christoph said, is very model dependent. So the calculation is non-perturbative. It's just to have an idea about the the possibility to have this monopoly on. So it's yeah. 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 The idea is if they both of them can decay into gamma gamma, so you can have a signal like light by light scattering, but then with a mediator or a resonance here. Okay, just to discuss, to not be late, about the experimental opportunities we have with, in CMS. So we are working now with 4 detector that we call Proton Precise Spectrometer that is placed far away from CMS. So we are putting the arms about 200 meters away from the interaction point here, because we expect that the intact protons will leave the interaction point with a very small angle going through this region here where we can catch these guys. So the momentum loss will be related to a very small angle that will be the trajectory from the interaction point. So we have been working with this prototype since 2016. I mean, 2015 we have some tests and some data. 2016 we have already data that can be analyzed, and in 2017 we have accumulating more data to analyze a few results that I'm going to present later. But the idea is that once we have a clear signal from 2 protons and the central system synchronized, you can be sure that we have a signal from an exclusive event, mostly by gamma gamma to some central system that will be producing CMS. So the idea is to have synchronization between the central detector and this 4 detector that will be placed here, 200 meters away. So here is just a schematic overview, just to explain that this 4 detector you'll be set up with 2 silicon trackers that you get the proton that is coming from the interaction point, which is on this side. They will be placed into these 2 places in red, and then you have after that a timing detector that I was talking this morning that will measure the time of flight of this proton from the interaction point to the CT-PPS apparatus. So with these 2 measurements, you can attain the proton to one event in the central detector. We have a very good resolution and the possible information to have all the kinematical reconstruction of this event. So the main variable that we are interested here is the momentum loss of this proton that is coming through the detector, which is measured with this Psi variable, and within the experimental acceptance we have here, we can achieve masses lying more or less from 100 GeV to 2 TeV. So this is the masses we are looking for, and this is the window that we can look for new physics. So with this newer data, I mean the latest data we have available to analyze, we look at for dileptons with this data of CT-PPS. So basically are the 3 possible mechanisms to produce dimuons in gamma-gamma physics, either the elastic case or the non-elastic case, where we have 1 proton associating or both protons associating. So in this analysis, the last one was used as background, and the other 2 are part of the signal. And in order to synchronize the measurement of these 2 muons in the central detector, and the proton in the 4 detector, we have to constrain the variables using this Psi measured in the mu-mu system, the Psi of the proton with the mu-mu system using this equation, which is relating the PT of the muons and the pseudo-rapidity of them. And then we can have a matching between the measurement in the detector, in the Raman pot that is placed with the silicon tracker, and the measurement for the central detector, looking for events that are within the experimental acceptance of CT-PPS. So you can see that you have 17 events observed that are in agreement with the CT-PPS acceptance. And from those 17, we have 12 events that we found to be signal of the gamma-gamma to mu-mu production. So the other 5 events should be background or something else. So we can use the the techniques we have applied in previous analysis. So all those CMS analyses I presented before can be used. The same ideas, the same strategy can be used to clean up the signal, which is here, the blue one, from Jarian contamination or dissociation, and try to really have the signal constrained, and you can clean up this part. So it's interesting that this approach we are applying with CT-PPS. So we have a central system with a tagged proton. Is very useful and very robust, even in a scenario with high luminosity. So that's the idea, to have these apparatus working for the high luminosity LGC in order to have these measurements with good sensitivity to keep studying the standard model or look for beyond standard model physics. So this is essential to have this matching between the protons and the central system in order to have a clear result of the exclusive physics. So here is just a Mario plot just to show the crossing from the information from the two sides we are using with the Raman plots of Totten, and we expect to have this single arm, so to say, measurement if you have the CT-PPS working one side, because we are going to put the time of flight detector or timing detector in one side, but you have both sides, you have this crossing area that we have a sensibility to look for masses in this range. So far we have one single arm that can have a limited above 200 or more or less GeV of invariant mass for these guys. So, but this depends on the LHC optics and the position of the Raman plot. So we have all the alignment of the detector in order to have sensibility to these guys. So, okay, to not go further in time, just to conclusions. So I've tried to present to you that we have some very optimistic predictions for light-by-light scattering in standard model. So we have a direct observation, or more or less a direct observation now by Atlas. So I expect that in the following years, or mostly following year, we can have more data in order to claim observation finally of this light-by-light scattering. So, and besides that, if you go to higher masses, we can expect to observe any evidences of beyond standard model physics. So there is a very good chance here to have a strategy, experimental apparatus that can allow us to have a deep investigation in this region, especially because we can look in more than one production channel. And basically with CT-PPS available and the data from the intact proton that you tag in the final state, you can have a very good sensitivity to these beyond standard model particles or theories that can show any deviation from standard model. So the idea is that even in a very complex scenario with high pileup, you can still use these experimental apparatus to measure the intact protons and still have sensibility to gamma-gamma physics. So we expect that in the following years, using CT-PPS and the strategy we have applied for the event selection, we can have some very substantial results, even for standard model or beyond standard model physics. Okay, thank you.